Section we will learn about maxima and minima of a function. So, and we will look at absolute maxima or minima, or they're called extremas, extreme points, which could be minimum or maximum, or relative, absolute versus relative. All right. So absolute means the absolute maximum value. So a function x squared plus 1, for example, right, does not have an absolute maximum value, because if you say, and you will say, oh, it's infinity, but infinity is not a value. There's no function, a point at x where you can say at this point the function has achieved its maximum value, because you can go further to the right and get a bigger value, right, if it's positive, and further to the left if it's a negative value. So, but it has a point here, right, at x equal to 0, the value is 1, and the value 1 is the absolute maximum of the function. Absolute minimum of the function, and there is no absolute maximum of the function. All right. So here, so there is something called an extreme value theorem, which basically says that if you have a closed and bounded interval AB, and you have a continuous function over a closed bounded interval AB, then it has a point at which an absolute maximum is obtained and an absolute minimum is obtained. Okay, so something interesting is, for example, if I give you a function fx equals x, and the domain is 0, 1. So obviously the function looks like this. And I'll ask you, what is the maximum value of the function obtained on its domain? And you will say, no, it doesn't, because you'll say 1. But 1 is not in the domain of the function, it's the open interval. So it has no maximum value in the domain. And same is true for the minimum value. So you'll say, okay, well, let's fix the domain. If the domain is 0, 1, but the function is as follows. So the function as a whole here goes up at 1, and here the value is, let's say, half. So the function is defined as f0 is half and is equal to x for all x belonging to 0 to 1. So this function again has a maximum at 1, but does not have an absolute minimum. You will say 0, but it doesn't achieve the value of 0, because at 0 its value is half. But you see, this function is not continuous, and in this example here, the domain was not a closed bounded interval. So the extreme value theorem basically says that if you have a continuous function in a closed bounded interval, then there will be a point at which it will obtain absolute maximum, and another point, or maybe the same point if it's a constant function, an absolute minimum. So here is x cubed. It's a continuous function, but the domain is this right here. So it does not have an absolute maximum or minimum. However, if you take any interval, any fixed interval, all right, a closed bounded interval like this, then the function will have a maximum at the end of the interval and a minimum, but not on R or not on open intervals. Now here it has an absolute maximum at 1, of 1 at x equal to 0, but no absolute minimum. Okay, here it achieves its absolute maximum value of 1 and absolute minimum value of -1, and it achieves it, you know, many different points, infinitely many points. Okay, here's a function. It's absolute. Let's see what the domain is. So domain is from 2 to 4, 0 to 4. 0 to 4 is the domain. The function has an absolute maximum of 2 at x equal to 0, and does not have an absolute minimum, because -2 is not obtained. And anything less than -2, there is a point which is lower than that. So no absolute minimum, but does have an absolute maximum. Here's a function. So it's a continuous function on a closed bounded interval, so definitely it will have an absolute maximum and an absolute minimum, and it does. maximum of 4 at x equals 4, and minimum of 0 at x equals 2. Now here this is not again closed and bounded interval because the 2 is open side, and you can see this one has an absolute minimum at 0 on its domain, but does not have a maximum because it gets closer and just keeps going bigger and bigger. So the limit here is actually to infinity, right? Okay, so that's the idea behind absolute maximums and minimum. So extreme value theorem says if f is a continuous function over the closed bounded interval AB, then there is a point in AB at which f has an absolute maximum over AB, then there is a point in AB at which f has an absolute minimum over AB. Now local extrema and critical points. So local maximum means that in the neighborhood of that point, that value is the maximum, locally, not absolutely. So for example, look at this function. So you will say at point 0, it has a local maxima. Because in the neighborhood, if you take a small interval, in this interval, this value is the maximum value of the function. So locally, there is an interval in which this point is the absolute maximum, relatively, okay, locally. Therefore, it's called a local maximum. And a local minimum at this point. Again, looking at its neighbors, it has the lowest value. It also has a local maximum here. But the function is not differentiable at this point. Why? Because the left-hand derivative is different than the right-hand derivative. For a function to be differentiable at a point, both derivatives, left and right, have to match. Slopes have to be, it has to have a slope at that point. So what we will see is that for a function that is differentiable, the points at which its derivative is 0 are called critical points, and the local maxima and local minima are found at critical points. Okay, if you have a local maximum for a differentiable function, then that point will be if it's a local maxima, that point will be a critical point. Okay, so that's what we will see, and we'll also see something more interesting. So local maximum and local minimum, or local extremum, means either one of the two, is that in a neighborhood of that point, it is the extremum value. So C, if it's an interior point on the domain of f, C is a critical point of f if the derivative of the function there is equal to 0. And if f is a differentiable function, from Fermat's theorem, if f has a local extremum at C and f is differentiable, then that point will be a critical point. Okay, because otherwise the slope would be positive or negative, and then you would find a point where the value would be greater and value would be lower, right? So the derivative has to be equal to 0. Okay, so here we have a critical point here, and that's a local maximum. We have a local maximum here, but it's not a critical point because the derivative is not defined. This is not a differentiable function. Here we have local minimum. Again, the derivative here is not defined because left and right derivatives are different. So again, it's not a differentiable function at that point. Here, f prime c, like for a cubic function, right? Cubic function goes like this, similar to this. So if you have a function x cube, take the derivative and make it equal to 0. So its derivative is 0 at x equal to 0 for x cube, f prime. So derivative is 0 at x equal to 0, right? But that point does not give you a local maxima or a minima. So that's a point of inflection. So that can happen. So just because it's a critical point doesn't necessarily mean that it has to have a local minimum or a maximum. The theorem, the Fermat's theorem, says the opposite. It says if there is a local maximum or a minimum on a differentiable function at the interior of the point, of the domain, interior, that means you have both derivatives, then that derivative has to be equal to 0. But not the other way around. Here the derivative is 0, but this is not a local extremum at all. Okay, here of course the derivative is not defined, it's a vertical line. So that's not a relevant example. Okay, how do you find the critical points of a function? Okay, and using graphing utility. So you can easily, of course, use GeoGebra here for plotting these functions. Okay, so here to find the derivative of this, f prime x is equal to x squared minus 5x plus 4. Make it equal to 0 and solve for x. So this will be x minus 4 minus 1. So minus 1 x minus 4 equal to 0, right? So that means x equal to 1 and 4. So they are the two critical points of this function. Yeah, and this one also do the same thing. Take the derivative and make it equal to 0. So each of the problems, what you have to do, you have to, so here is the plot of the function, and you can see at x equals 1 and x equals 4, the derivative is equal to 0. Now something interesting I want to tell you right now. Look at this point where you have a local maximum. So what is happening to the slope? Slope is equal to 0 at that point. However, as you move from left to the right, the slope on the left was positive, and as you move it becomes 0 and then it becomes negative. So what is happening to the slope? The derivative? The derivative is decreasing. That means at this point, the second derivative of the function, which means the change of the first derivative, should be negative. Okay, so here we found f prime x to be this function at x, and at x equals 1 and x equals 4, this will be equal to 0. But what about the second derivative? So find the second derivative of the function, which is 2x minus 5, and plug in x equals 1. So at 1, f double at 1 is negative 3. It's negative. So slope is decreasing. That means it's a local maxima. Here we have a local minimum, critical point, derivative is equal to 0 at x equals 4. What about the second derivative? The formula is 2x minus 5. Plug in 4. So 2 times 4 is 8. 8 minus 5 is 3. So it's positive, and you can see that. Slope to the left-hand side of the critical point is negative, and then slope is increasing as you move to the right of x equals 4. The slope here is positive, slope here is negative, and it's 0 here. So it goes from negative, 0, positive. So it's increasing. So for a local minima, second derivative greater than 0. For a local minima, second derivative less than 0. So when you are given a function, find the formula for its derivative, make it equal to 0, solve the equation, find the critical points, and at each critical point you can try the second derivative and see if you get a sign. If second derivative is also equal to 0, then it could be, it doesn't tell you whether it's a local minima or a local maxima. Okay, the second function, x squared minus 1 cube. So here fx was x squared minus 1 cube. The derivative using chain rule is 3 times x squared minus 1 squared times derivative of the inside, which is 2x. So you get this function. Now make it equal to 0. This becomes equal to 0 at x equal to 0. Here the derivative is 0, x equal to 0. And then x squared minus 1 should be 0, which means x squared is 1, so x is plus minus 1. So this point and this point. And you can do the second derivative of this, and you'll find that second derivative here, see on the left hand side, negative slope becomes 0, positive slope will be greater than 0. But these points are inflection points, and you can see that. And the reason for that is, of course, the cubic function. So we have inflection points. So these two, negative 1 and 1, are neither local or extremum, local minimum or a maximum. Okay, so no local extremum at 1 or negative 1. So you can see derivatives are extremely important for optimization, to find the best value. And optimization is something that we do in everything in life, right? In everything. Every time you want to find the best price, the best design the strongest material, or whatever, even in our daily life, in our relationship, in social engineering, we want the best results, right? In politics. So an optimization is what we are after. And what gives us optimization? What technique can we use? Calculus, differential calculus, taking derivatives of the functions. And similarly here, the third function is 4x over 1 plus x squared. So apply the u over v formula. So we have a denominator v squared and then v du minus u dv, we get this function. To make it equal to 0, the top has to be equal to 0. 4 minus 4x squared has to be equal to 0. And that gives us x is plus minus 1, because 4x squared is equal to 4. 4 cancels, x squared is 1, x is plus minus 1. And you can plot the function, and also you can take the second derivative at plus 1 and minus 1. And you can see clearly here the second derivative will be negative, and here the second derivative will be positive because slope is increasing. Okay. Now, what about, so derivatives are giving us local extremas. What about absolute extrema? We're given a function, how do we find the absolute maxima? So now, if let f be a continuous function over a closed bounded interval, then the absolute maximum of and the minimum will occur at endpoints of I or at a critical point of f in I. It has to be differentiable, of course, because critical points means a point where it's differentiable. So there's a slight typo in this theorem. Okay. So as an example, a simple example, when we had the function in the closed and open interval, 0, 1, and the function was simple, equals x, we don't have any critical point. Derivative of x is 1. You equate it to 0, you get nothing. Right? 1 equals to 0 is meaningless. So derivative will not be equal to 0, but the absolute maxima is found at the endpoint, and absolute minima is also found at the left endpoint, and maxima at the right endpoint. And that's what the theorem is saying. So if you have a differentiable function in a closed bounded interval, find all the local extrema points, and then also look at the end values, and then choose the maximum value for absolute maxima, and choose the minimum value for absolute minima. Okay, so we are given this function. It's a quadratic function over a closed and bounded interval. That's good news. Okay, so we will find f1 and we will also find f3. So keep track of this. Now in step 2, we find the derivative and make it equal to 0 to find critical points. So we get only one critical point when we solve that equation. Now this is also a candidate for absolute extremum. So let's evaluate f of 3 over 2 and we find 1/4. Now we look at 3 points, this, this, and this. The maximum value of the function is 1/4, obtained at 3 over 2, and the minimum value of the function is -2, obtained at f of 3. Okay, right here. So here is the minimum value at the extreme point, but the maximum value was at a critical point where the derivative was equal to 0. And that's the technique that you have to apply for all functions. For example, this function, this is also a quadratic function. So you'll find the value of the function at 1, at 4, make the derivative equal to 0, 2x minus 4 equal to 0, which means x equals 2. So compare the value of the function f1, f2, and f4, and choose the maximum value and the minimum value from these three. All right, that finishes the section on optimization using different derivatives.